Section: Introduction. In this section, we discuss the importance of language model, LM, scaling and understanding model capabilities and their impact on various tasks and post-training techniques like chain of thought. We aim to comprehend and predict LM behaviors across different scales, benchmarks, and algorithmic interventions, which is a key concern for many researchers and engineers. By analyzing scaling laws, we can gain insights into how LM performance scales with computational measures, such as training flops, and downstream capabilities like perplexity and benchmark performance. However, many benchmarking and post-training studies lack scaling analyses due to limited computational resources and training models at only a few scales. In our work, we propose observational scaling as a cost-effective alternative to traditional scaling approaches. We suggest that the performance of an LM is determined by a few key capabilities, such as natural language understanding and reasoning, which can be efficiently converted from training compute. By examining existing LM benchmarks, we identify capability measures that exhibit scaling relationships within model families and across different models. Observational scaling offers advantages in terms of cost, resolution, and coverage by utilizing a wide range of existing models without additional training costs. It allows us to study complex capabilities and compare different scaling strategies across diverse model families. By selecting representative model families, we can make accurate scaling predictions for benchmarks and post-training interventions using a small number of models. Our findings demonstrate that observational scaling can predict emergent and agentic capabilities of LMs, as well as the effectiveness of post-training methods like chain of thought. We establish log-linear relationships between compute, capability measures, and downstream metrics, providing a valuable framework for understanding LM scaling. Section Summary. In this section, we introduce the concept of language model, LM, scaling, which is crucial for understanding model capabilities and the effectiveness of post-training techniques like chain of thought. Our work focuses on predicting LM behaviors across scales and benchmarks, aiming to provide insights for researchers and engineers on how algorithmic interventions and complex capabilities scale predictably with model size. By leveraging observational scaling laws, we demonstrate that it is possible to make accurate scaling predictions on various LM capabilities, such as emergent and agentic behaviors, and post-training methods, even with weaker models, offering a cost-effective and straightforward approach for future scaling analyses. Section: Related work. In this section, we will discuss the related work on compute scaling laws. In standard scaling laws, the scale is determined by the compute resources allocated to train language models, LMs, such as the number of training operations, model parameters, and training tokens. Scaling laws usually describe a power law relationship between the cross-entropy loss of LMs and their compute scale measures. These relationships can take different forms, such as a function of model parameters and training tokens, or a function of compute resources. The parameters in these relationships are determined by training LMs across different compute scales and measuring their loss. Our work differs from traditional compute scaling laws in that we focus on scaling laws for post-training performance rather than pre-training. We are interested in understanding how the performance of models changes after training across different model families and using observable measures other than compute resources. Scaling laws have been extended beyond pre-training loss to analyze transfer learning and downstream performance in various domains. There is evidence suggesting that the performance of LMs on downstream tasks is linked to factors like model size, but whether this relationship can be predicted accurately with scaling laws is still debated. Research has explored the challenges of predicting benchmark performance due to factors like rapid changes in performance and the metrics used. Some studies have proposed using scaling laws derived from pre-training loss or computational measures to predict benchmark performance. Correlations between different benchmarks have also been studied extensively. Researchers have looked into the relationship between out-of-distribution and in-distribution performance of machine learning models. In the field of natural language processing, NLP, and LM benchmarks, strong correlations have been found between different evaluation metrics. Our work also observes benchmark correlations and low-rank structures but focuses on using these properties to make scaling predictions for benchmark and algorithm development. In this section, we introduce our observational scaling laws that generalize standard compute scaling laws. We aim to extract a low-dimensional capability measure for LMs from their benchmark performance, which shows a log linear relationship with compute scale measures. This capability measure can be used for scaling analysis of complex LM capabilities. In standard compute scaling, there is a proposed power law relationship between models' compute measures, such as training operations, and their errors, like perplexity. This relationship allows us to make inferences about a model's performance at future compute scales by extrapolating this relationship. However, fitting such scaling laws can be challenging due to the unique scaling coefficients for each model family and downstream benchmark. This means that scaling experiments are often limited to a few models within the same family, and predictions are specific to the scaling strategy used within that family. Section Summary. In this section, we introduce a novel approach that generalizes standard compute scaling laws by deriving a low-dimensional capability measure for language models, LMs, from their observable benchmark performance. This measure exhibits a log linear relationship with compute scale measures, serving as a surrogate scale for analyzing complex LM capabilities. Unlike traditional compute scaling laws that focus on training resources and pre-training, our method aims to build practical scaling laws for post-training performance across multiple model families using standard benchmark metrics. Section: Observational Scaling. In this section, we propose the idea of a simplified measure for language models, LMs, that connects computational power to their capabilities. This measure can be derived from common LM benchmarks. We suggest the existence of a capability vector for each model, which can be represented in a low-dimensional space. By analyzing errors on various benchmarks, we aim to find a relationship between model capabilities and computational efficiency. This relationship is expressed through equations that involve different parameters. These equations help us understand how different LM families convert computational resources into capabilities. By combining these equations, we can generalize the scaling relationships for a single model family. The shared capability vector, S_M, represents the core abilities of a model, while the efficiency parameter, theta_F, reflects how well each model family utilizes computational resources. This approach allows us to estimate the model capabilities based on observable benchmark results, making our analysis more reliable. We can apply this method to a wide range of LM models, even those with limited public information. We aim to validate our proposed equations in the following subsections. We will first confirm the relationship between model capabilities and benchmarks, then explore the efficiency of different model families in converting compute into capabilities. Finally, we will present our algorithm for estimating model capabilities based on the provided framework. To validate the existence of a low-dimensional capability measure that correlates with LM benchmarks, we analyze the principal components of the benchmark data. By showing that only a few components capture most of the variation in the benchmarks, we support the idea of a simplified capability space. Our analysis includes a diverse set of LM models across various training methods and a wide range of benchmarks assessing different LM capabilities. We carefully selected these models and benchmarks to ensure the robustness of our findings. Our collection of LM models includes a variety of publicly available models from different model families. These models have been trained using various methods and cover a broad spectrum of LM capabilities. We focus on pre-trained base models to maintain consistency in our analysis. Additionally, we include an analysis of instruction-tuned models, including proprietary ones like GPT-4, to validate our approach further. For benchmarking, we gathered a comprehensive set of evaluation metrics that assess different aspects of LM performance. These benchmarks cover general knowledge, reasoning abilities, programming skills, multilingual capabilities, and more. We source these benchmarks from standardized evaluation protocols to ensure comparability across different LM models. Our data collection process is detailed in the supplementary materials for reference. Section Summary. In this section, we propose a low-dimensional capability measure for language models, LMs, that can be extracted from observable standard LM benchmarks. By validating the existence of a capability vector that linearly relates to LM benchmarks, we show that only a few principal components of the benchmarks capture most of their variation, supporting our hypothesis. Our analysis includes a diverse set of 77 models across 21 model families and various benchmarks assessing different LM capabilities, demonstrating the robustness and applicability of our proposed capability measure. Section: PCA Analysis. In this section, we obtained benchmark metrics for the language models, LMs, and dealt with potential missing values using PCA imputation. We then used PCA to extract principal components, PC, as measures of LM capabilities. These PC measures are low-dimensional and show that a few key PCs can explain a large portion of the variance in the benchmarks. We found that the first PC alone can explain a significant amount of the variation in LM capabilities. By analyzing these PCs, we identified that they represent different aspects of LM capabilities such as general capability, reasoning capability, and programming capability. Our results suggest that many LM capabilities can be expressed as a combination of these principal capabilities. We also showed that the extracted PC measures scale log linearly with training flops within each model family, indicating a generalization of compute scale across different models. Furthermore, we demonstrated a linear correlation between the PC measures and training flops for models within each family. This correlation holds for various model families, supporting the idea that models share a common capability space. To make our scaling analysis more interpretable, we defined a procedure to estimate the scaling relationship and fit regression with PC measures. By mapping the extracted PCs into a scalar capability measure, we can express capabilities in units of flops, making the analysis more intuitive. In summary, our findings support the idea that LM capabilities can be represented by a few principal components and that there is a relationship between these capabilities and the computational resources required. Section Summary. In this section, we utilized PCA analysis to address missing values in our benchmark metrics for language models, LMs. By extracting principal components, PC, from evaluation metrics, we found that the top 3 PCs explain a significant portion of the variance, with the first PC alone explaining nearly 80% of the variation in LM capabilities. These findings suggest that LM capabilities can be represented by a few key, principal capabilities that scale log linearly with training flops, supporting the idea of a shared capability space across different model families. Section: Validating. In this section, we assess the effectiveness of observational scaling laws by demonstrating their ability to accurately predict how LMs scale across complex and unpredictable phenomena, such as emergent phenomena and agentic abilities. These scaling laws also help us estimate the effectiveness of techniques like chain of thought. To ensure the predictive power of our scaling laws and avoid overfitting, we conduct experiments with systematic holdout sets and robustness checks. We pre-register our predictions for future models to test if our scaling laws overfit current models. Our code, including implementation and data, is available at the provided link. For extracting PC measures, we set the number of PCs to 3 as it captured around 97% of the variation in benchmark performance and consistently performed well across our experiments. We used the Llama 2 model family as a reference for capability equivalent scale transformation. To enhance interpretability and visualization, we utilize the accuracy metric, y equals 1e, for fitting the scaling laws and creating plots. To validate our scaling laws, our main goal is to assess how well they fit the data and can predict from smaller to larger models. We conduct systematic holdouts on a test set, splitting models based on scale or capability into weaker and stronger ones. We fit the scaling law on weaker models and test its predictions on stronger ones. Pre-processing steps are applied only to the training set to prevent any data leakage. We compare our scaling predictions with compute-based scale measures like training flops and model size using mean squared error, MSE, on the holdout set as the main evaluation metric. We pre-register all functional forms for the fitted scaling laws in our experiments for future models. We commit to updating the manuscript with prediction results after testing on models developed post-May 2024. Our findings support the observational approach to scaling laws and suggest that higher resolution scaling laws can enhance our understanding of scaling phenomena for LMs. We conducted tests on 4 big bench tasks labeled as emergent, including arithmetic and non-arithmetic tasks. For arithmetic tasks, we adjusted the cutoff to avoid trivial prediction tasks. Additional results on more tasks are provided in the appendix. Section Summary. In this section, we validate the usefulness of observational scaling laws by demonstrating their accuracy in predicting the scaling behaviors of language models, LMs, across complex phenomena like emergent capabilities. We ensure the predictive nature of our scaling laws by designing experiments with systematic holdout sets and robustness checks, pre-registering predictions for future models, and comparing our scaling predictions to existing compute-based scale measures. Our findings support the observational approach to scaling laws and suggest that higher resolution scaling laws could enhance our understanding of scaling phenomena for LMs, particularly in forecasting transition points between model performance levels. Section: Prediction Results. In this section, we present our prediction results using our PC measures compared to the baseline prediction method based on training flops. We discovered that our PC measures can accurately predict capabilities, even for poorly performing models. On the other hand, using training flops led to poorer extrapolation on the test set and better fits on the train set, with much higher MSE values. This discrepancy is likely due to the differences in training flops across various model families. Additional results on the model size baseline can be found in the appendix. We are interested in developing autonomous agents using LMs, with examples like AutoGPT, Devon, and SWE agent. Although these agents still lag behind human-level performance on challenging real-world tasks, there is optimism that larger-scale models in the future will greatly improve their capabilities. However, there is uncertainty about how well existing models trained for language and code tasks will transfer to agentic tasks that involve taking actions over multiple rounds. We analyze the scaling properties of ELM's agentic capabilities and backbone model capabilities to show that agent performance can be predicted from simple benchmark metrics. We tested on 2 standardized agent evaluation benchmarks, Agent Bench and Agent Board, which consist of various tasks for evaluating ELM's agentic capabilities. We used aggregated metrics provided by these benchmarks for prediction. We included models evaluated on each benchmark, covering open instruction-tuned models like Llama 2 Chat 2 and Vicuña, as well as proprietary models like GPT-4 and CLAUDE-2. Our analysis showed that agent performance can be predicted accurately from models with much weaker performance, indicating a strong correlation between the complex agentic capabilities of LMs and their base model capabilities. We visualized the weights assigned to the base evaluation metrics on both benchmarks, derived from regression weights fitted on PC measures. These weights highlighted the importance of programming capabilities, general knowledge, and reasoning capabilities in defining ELM's agentic capabilities. When researchers introduce new post-training techniques to enhance pre-trained models, it is crucial to understand if these improvements will persist across models and scales. We demonstrated that it is possible to make reasonably accurate predictions on the effectiveness of techniques like chain of thought, COT, and self-consistency, SC, as model scale increases. Our approach involved fitting observational scaling laws based on base model performance and performance with the post-training intervention, revealing the scaling efficiency of the intervention. Section Summary. In this section, we present our prediction results using performance measures for predicting agentic capabilities of language models, LMs. We find that these capabilities can be accurately predicted using our measures, even for models with poor performance, unlike when using training flops which result in poor extrapolation. Our analysis shows that agent performance is highly predictable from simple benchmark metrics, indicating promising scaling properties of LM-based agent capabilities as backbone LMs continue to scale up. Section: Setup. In this section, we tested the effects of post-training techniques COT and SC on the GSM-8K dataset, along with additional results on Big Bench Hard with COT. We excluded GSM-8K from the base metrics to prevent making prediction tasks too easy. We used various pre-trained base models, including those specifically trained for code data, and applied a default flops cutoff for holdout validation. For COT, we compared prompting using 8 reasoning examples with naive prompting using only a few shot examples. For SC, we sampled 5 COT reasoning paths at a specific temperature to aggregate final answers and compared it with a single sampled COT answer. Our predictions showed that the performance of stronger, larger-scale models with and without post-training techniques can be accurately predicted from weaker, smaller-scale models. However, predictions based on compute scale measures like model size and training flops are less reliable. The scaling trends between COT and self-consistency with COT differ, with COT showing a more pronounced scaling trend. We visualized the important capabilities for post-training intervention using regression weights mapped to base capability benchmarks. Moving from naive to COT, we observed higher weights on enhancing general knowledge and code, leading to greater improvements compared to enhancing common sense. These analyses help understand how different post-training interventions affect scaling recipes for code models versus general-purpose LLMs. To make scaling analyses more accessible, we identified a small set of models that maintain high prediction accuracy while reducing evaluation cost. We used optimal experimental design theory to select an optimal subset of models for regression problems, considering a constraint on the maximum number of models to choose. By conducting a structured search over model families, we found an optimal subset under the budget constraint. We validated our selection method by replicating our scaling analysis using a small subset of models selected by our method. Our v-optimality selection method outperformed random selection and quickly converged to the prediction performance of using the full set of models. Using a small subset of models selected by our method, the fitted scaling curves effectively captured the scaling trends of different post-training methods. Section Summary. In this section, we tested post-training techniques COT and SC on GSM-8K and Big Bench Hard datasets, excluding GSM-8K from base metrics to prevent trivial predictions. We included various pre-trained base models and applied default flops cutoff for validation, comparing COT prompting with reasoning examples to naive prompting. Our results show that predicting performance of stronger models from weaker ones is more accurate using post-training techniques rather than compute scale measures, with COT demonstrating a more pronounced scaling trend compared to self-consistency with COT. Section. Recommended Model Series for Scaling Analysis. In this section, we present a recommended series of models for scaling analysis. We have compiled a list of models that represent different budget constraints, including the popular Llama 2 models. These selected models cover a wide range of capabilities and dimensions to capture various scaling aspects. For instance, under a 12-model budget constraint, we have included models like Llama 3, Falcon, and DeepSeek Coder to represent both strong and weak models with specialized programming capabilities. Our research confirms the idea that there exists a low-dimensional space of LM capabilities that can be captured through a low-rank decomposition of existing LM benchmarks. While our main focus is on scaling laws and predictions, we also explore how these shared capabilities can be used as evaluation metrics and optimization targets for LMs. We find that PC1 is a smooth capability measure with a high dynamic range, unlike many existing benchmarks that have limited ranges. PC1 allows us to compare models across different scales effectively. This makes it a potential optimization target for pre-training, where interventions can be benchmarked against PC1 at small scales and validated at larger scales. Furthermore, by using PC1 as a unified measure of capabilities, we can compare compute efficiencies across various model families. Most models show a clear pattern in the trade-off between training compute and capabilities, with some outliers like the Phi family, which may use additional inference flops for generating training data. We also explore the interactions between post-training techniques and model families by projecting scaling curves to compute equivalent flops for different families. This analysis helps us identify which model families benefit the most from these techniques and at what point they start to benefit. Models like Phi and DeepSeek Coder exhibit unique behaviors compared to others, emphasizing the role of pre-training data in determining model scaling behaviors. While our focus was not specifically on these analyses, we believe that our approach can provide insights into the differences between LM training methods and their scaling behaviors for future research.